Hello, everyone. It's a pleasure to be back. Today I'll be talking about my work on the approximation resistance of balanced linear threshold functions. So the main result of this work is that there exists a predicate which is a balanced linear threshold function which is unique games hard to approximate. And this refutes a conjecture made by Ostrin, Benebes, and Magin, who conjectured that all predicates of this form are approximable.
Better than random, you mean?
Exactly. I'm going to get to that, but better than random. That's exactly correct. Okay. Yeah. So what does all this mean? So let's start with balanced linear threshold functions. Okay. So recall that a linear threshold function is a function, so I'll take it from plus or minus 1 to the k to plus or minus 1. Which has the form so we take a linear form, a linear function of the input, and then we just check whether it's positive or negative. If it's positive, then we output 1. If it's negative, we output minus 1. And we'll want to require that this. We'll want to require that we never have 0 here. Okay, and then we say a right. I'll abbreviate this as LTF. So we say an LTF is balanced if there's no constant term. Exactly. So if f is a balanced LTF, then for all x, f of minus x is minus f of x. Okay, so here are two nice examples. So the first is majority. So if k is odd, f of x1 through xn equals, oh, sorry, k, yes. Thank you. Equals the sine just the sine of the sum of the xi's. So for odd k, the majority function predicate on x1 through xk is a balanced LTF. Here's a second. Here's a second example, monarchy. So if we take f of x1 through xk equals, or to be the sine of k minus 2 times x1 plus the sum from I equals 2 to k of xi. So how will this function behave?
Well, if everyone else votes to overthrow x1, then
yeah, exactly. The monarch x1 gets his or her way unless everyone else votes to overthrow the monarch. Okay, so these are examples of balanced linear threshold functions. Okay, so now now let's talk about approximation resistance. Okay, so here we'll consider a single predicate P. And then here we're considering constraint satisfaction problems. Right. Which I'll abbreviate as CSPs, where all constraints are of the form P. So yes.
Function. Just a function. Yeah.
Okay. But yeah, I think instead of giving a precise definition, I think I'll illustrate it with the key example 3-sat. So here, Okay, so right, as you likely know already, in 3-sat, we're given a bunch of clauses where each clause is the OR of 3 literals, either not xi or not xi, and then we're trying to satisfy as much of them as possible. Right. So here the predicate p is just p, just the OR function. Okay, yes. So more generally, we have a single function p on k inputs, and then all of our clauses have the form where there are n variables overall. We choose some k of them. And we can also negate them. But all the clauses have that form.
It's a bunch of constraints of the form P.
Yes.
So in this case, k is 3?
Yeah.
In this case, k is 3, exactly. Okay, so so in general, castrate satisfaction problems are extremely hard to solve. But we can still try and satisfy as many of the constraints as we can. So the most trivial algorithm is just to guess an assignment at random. Okay, right. So if we did this for 3-sat, what proportion of the clauses would we satisfy? No.
It's an OR function.
And they're on distinct variables.
Oh yeah, assuming that they're on distinct variables.
Yeah.
Yes. So for 3-sat, it's okay, but then a natural question is, can we do better? So okay, so we say a predicate p is approximable if given a CSP such that here there exists an epsilon bigger than 0, such that given a CSP such that 1 minus epsilon of the constraints are satisfiable. we can find an assignment satisfying RP plus epsilon of the constraints, where RP is the proportion satisfied by a random assignment.
That's the probability that P equals 1.
Yeah.
Yes, that's fine.
Okay, yeah. Right, and otherwise we say it's approximation resistant.
Important that the epsilon is the same epsilon in both quantities, 1 minus epsilon and
It's
RP.
important, but you might have
It may as well be, yes. Yeah, it is important that both of them are constants which are strictly bigger than 0. Let's see. Other questions before I continue?
I know you're going to get to this, but can you motivate why you want to do it? I mean, so we have a parity that's balanced and 4 that's a threshold. Like, why is it important to show the hardness of a threshold function that's balanced?
Okay, yeah. So I will get to this, but the reason that this particular class is interesting is because it's one of the simplest classes for which very little was known previously, and a major reason for that is because it can't have a balanced pairwise independent distribution of solutions.
Yeah, you'll get to it.
But yeah, I will get to this.
When you say we can find, you mean
Efficiently.
deterministically. Oh, no.
So when I say we could find, like, I mean a randomized polynomial time algorithm. But yeah, I do mean efficiently.
So the trivial algorithm is that one.
Yeah, to get a single mode.
You can lift it if you want. I mean,
I'll save that for later. Okay, so here, so returning to 3SAT as a key example. So host odds, 3-bit PC probabilistically checkable proof showed that 3 XOR, which is just the predicate, to the product of these 3, like x1, x2, and x3, and 3SAT are NP hard to approximate.
different statement than the approximation resistance you make. So it's I think the approximation
yeah,
resistance, you have an assumption that many of
exactly. So the approximation resistance, assuming that P is not equal to NP. So here, for our main result here, we should, it implies that this predicate is hard to approximate, assuming the unique games conjecture and P is not equal to NP, or at least that unique games can't be solved in polynomial time.
Yeah. No, I was pointing out to another difference. In the approximation resistance, you assume that there's 1 minus epsilon fraction of the constraints are satisfied. For Hastad's result, you just can say that you cannot approximate it better than without any assumption. You cannot approximate better than additive epsilon unless P equals that. Right.
Yes. Yes.
So I'm not sure. So does that statement, Hastad's statement, say that then is it implying that those two examples are both approximation resistant?
Yeah.
Yes.
That's the easy.
Yes, exactly. So assuming P is not equal to NP, 3 XOR and 3 SAT are approximation resistant. Yes. Okay, so when I that's what balanced linear threshold functions are, and this is what approximation resistance means. Right. So when I first heard about this problem from Per and Johan, my first thought was, wait a minute, didn't Raghavendra solve this in 2008? Well, here's what Raghavendra showed. So So Raghavendra showed the following dichotomy. For any predicate P, either one of two things happens. So either a standard SDP, which I'll describe shortly.
Semidefinite program.
Yes, where SDP stands for semidefinite program. So either a standard semidefinite program distinguishes between the case when at least 1 minus epsilon of the constraints are satisfiable, and at most RP plus epsilon of the constraints are satisfiable. Or for all epsilon bigger than 0, it's unique games hard to distinguish between these two cases. Okay, and here I've written the unique games problem and the unique games conjecture here, but here I'm actually going to use this as a black box.
Yeah, it's probably worth stressing how amazing this result is, in that there's just one algorithm for all these various different optimization problems that gets you the best you can get, the standard SDP.
Yes,
assuming
unique games conjecture, or at least the unique games is hard to approximate. Sorry, unique games is hard to solve. I'm saying hard to approximate 2 times. Okay, so. Okay, so what is this? What is the semidefinite program? Okay, so here, for simplicity, I'll focus on the case when the semi-definite program thinks that everything is satisfiable. So it what it does is it searches for global for global biases and pairwise biases, BI and BIJ. And then it checks each individual constraint to confirm that there is a distribution of satisfying assignments which matches the global biases and pairwise biases. Okay, so let me illustrate this with let me illustrate this on 3 XOR. Okay, so let's just take the 2 constraints x1 times x2 times x3 equals 1, and x1 times x2 times x3 equals -1. Okay, so it's clearly impossible to satisfy both of these at the same time. However, this SDP can take can take the global biases and pairwise biases to all be 0. And then
you did not define the BI and BIJ.
Ah.
So the biases of the bits and the pairs of bits.
Right. So a BI is supposed to be the expected value of xi. Thank you. And Bij is supposed to be the expected value of xi times xj.
In that distribution. In the distribution of assignments that you are looking for.
Yes. And in fact, globally, so yes. So I say that they're global because there's supposed to be like just an assignment distribution of solutions which has these biases. But all the SDP is checking is that if we consider each constraint individually, there's a local distribution which has these biases and pairwise biases. Okay, so here for the constraint that x1 times x2 times x3 equals 1, if we take the uniform distribution on these four solutions, all the biases and pairwise biases will be 0. And if we now look at the individual constraint x1 times x2 times x3 equals -1, then right, if we just reverse all the signs, this distribution of solutions still has biases and pairwise biases, which are all 0. So the standard SDP thinks that both of these are satisfiable.
So there exists such a distribution, the uniform distribution. Right? You say that the SDP checks whether there exists a global distribution.
Per constraint.
Yeah, and checks it
sorry.
checks it on every constraint.
Yes, checks.
Checks it on every constraint, and the distribution is 1. Or local.
Yes, it's a local distribution on just on the variables of the constraint.
It's a projected distribution on the local bits, or it's just a distribution. If you just look at the distribution on each constraint separately on the variables of this constraint, you might as well look at the predicate. You want a global distribution that when the biases on the bits of each constraint.
So here I want global values, bi and bij, such that if I look at each individual constraint, there's a local distribution of solutions on that constraint, which has these, where the expected value of xi is bi, and the expected value of xi times xj is bij.
Why do you need the CSP then? This looks like something to
the
check.
xi's play a role, right? Like the bi's depend upon which xi's show up in this clause.
Yes, exactly.
And is the confusion why you're using the word global?
Oh, you mean the BIs can be different for each? Yeah, okay, so they're very good. Yeah, so it's good. Yeah. So in this sense, it's below. Yeah. Okay. Okay, very good. Yeah.
Okay, yeah. So an important special case is when we can take all the bi's and bij's to be 0. I think at this point I'll erase this part here. Okay, so as first shown by Osher and Mosel, so if if P has a balanced has a balanced pairwise independent distribution of solutions, then as we just saw here, we can take all the biases and pairwise biases to be 0, and P is unique games hard to approximate. OK, so here I'll just make a quick remark. There's a gap between like what's known for what's known which predicates are known to be unique games hard, and which predicates are known to be NP hard. So NP hardness. So as shown by Xion Chan. If P has a pairwise independent subgroup of solutions, then it's NP hard to approximate.
Subgrouping F2 to the N, the subspace.
Yes.
So could you explain a little more? The subgroup of solutions.
OK, so
Support of this distribution is uniform on a subspace of 0, 1, 2, 3.
For each predicate, it's the same.
It's the same condition, but it's just an extra condition on.
Different subspace, but it's always.
No, in this case,
So
it's still in this case, in the 0 bias case. And so all BIs are 0, it's just a condition on P, not on the P.
yes, so like, both of these are conditions on P. So in this one, it has to be right. It has to be a subgroup, which over plus minus 1 to the k means it has to be a subspace.
But it's obviously different for each predicate.
No, they are the same.
It's a single.
It's the same for all the local ones.
So over there, it was.
Because the BIs may not be 0. For different bits, you may have a different bias in general. But in this case, when they are 0, it's 0 for all bits, so it might as well be a constraint on P.
Yes, but here, if unique games hardness, it just has to be a distribution. It doesn't have to be a subspace. OK, so right, and here I'll also remark as I briefly remarked earlier. So part of what makes this class of balanced linear threshold functions interesting is that it can't have a balanced pairwise independent distribution of solutions. So this criterion is not enough. So before I describe what criterion we use and sketch how we construct such a predicate, I'll first describe an example which is approximable, the majority function. Okay, so so how do we approximate majority? So how we do it is that the SDP, there actually in fact here a linear program is sufficient. So our SDP is going to give us biases BI. And again, the idea is that the expected value of xi should be BI.
You're going to say what the linear program is? It's the obvious one where you just constrain the variables to be between -1 and 1?
Yes. So here, okay. Although like it's a bit trickier to say how the constraints are evaluated though.
But it's a natural linear programming relaxation of the system.
Okay, so the so what we'll do is given these biases BI.
Maybe just one word about this linear program. Just you want variables to be plus and minus 1, and you say it's a linear program. Say they are between -1 and 1, let's say. And the linear program gives you the best approximation using these fractions. And then the question is, what do you do with these fractions?
Yes.
Yeah, so that's what you.
Yeah, that's exactly what I'll do here. So take for all I, flip. So independently flip a random coin. With bias epsilon BI, where epsilon is a sufficiently small positive constant. Right, and then take and then we'll take xi to be 1 if the coin comes up heads, and -1 if it comes up tails. Okay, so then, yeah, 1 and -1. And then the key observation, so the expected value of xi is just going to be the expected value of xi after rounding is going to be epsilon times bi. The expected value of xi times x, and then because these are independent, so if we look at the expected value of xi times xj, that'll be epsilon squared bi bj, and so on. So now, So now what we'll do is we'll use Fourier analysis on the majority predicate, which here is just a fancy way of saying we'll decompose it in the monomial basis. So for example, for k equals 3, majority of x1, x2, and x3 is x1 plus x2 plus x3 minus x1, x2, x3 divided by 2. OK. So in general, if you do this for a larger k, I forget what the coefficient is, but it's not too hard to compute. You'll get some coefficient c1 times the sum times the linear term. Plus higher order terms. And this means if we take the expected value of the majority predicate after rounding, then what we'll get is we'll get c1 times epsilon times the sum of the biases plus O of epsilon cubed. And now we're basically done by the following claim. We have to have that the sum of these biases is at least 1. And the reason for that is that and the reason for that is that in order for this constraint to always be satisfied over our entire distribution of solutions, we always have that the sum of the xi's has to be at least 1, and this means the expected value of the sum of the xi's, which is just the sum of these biases, has to be at least 1.
Here these xi's are in the linear program, not before rounding. And also,
yeah, this here is before rounding. So the linear program gives us these values bi, and then after rounding by flipping these coins with bias epsilon times bi. Like, if the linear program indeed thought that all the constraints were satisfied, this says this says after rounding, each individual constraint is satisfied with probability strictly greater than 1/2. And this shows that majority is approximable.
what is the best you can do? What's the best that we know how to approximate the CSP for majority?
Let's I don't know off the top of my head. I think I think if we use this rounding scheme, then like this constant becomes exponentially small. Sorry, no, not exponentially small. Right. I think majority is right.
A majority of 3 bits. I mean, just for 3 bits, what's the best estimation you can get for majority?
But for majority of three bits, yeah, I don't know off the top of my head.
The trivial algorithm gives 1/2, and you get some bigger one.
Yes. Okay, so in the last few minutes, I'll describe the criterion we use in Sketch, and sketch how to construct our predicate. Before I do, what questions are there on everything so far?
So just to get sketch, you're going to show approximation resistance by showing that this SDP fails to
Yeah.
distinguish.
Yes, I'll construct a predicate which is unique games hard to approximate by constructing the predicate so that this SDP fails. So yes, exactly. It'll think everything's satisfiable, whereas in reality, in fact, you can't do any. You can't actually deviate from random. And then I'm using Raghavendra's result as a black box to say that its unique games hard to approximate.
So just to clarify the pairwise balanced ones, the rounding scheme that you would use is it the same?
So if P has a balanced pairwise independent distribution of solutions, then essentially the SDP is giving no information because it's just saying 0 for everything.
Will not
No,
happen in
I'm
majority.
talking about the case, so either so the Raghavendra's theorem said one of 3 things happen. Either it's always uniquely hard, or the one case you can get an RP plus epsilon scheme.
Right. So it's a dichotomy saying like either the SDP can do better than random, or either the SDP can distinguish the cases, or its unique games hard to do so. So if P has a balanced pairwise independent distribution of solutions, then like the SDP fails to distinguish it, because then we can take the global biases to be 0 and choose the constraints completely at random.
Wait, so I'm talking about the positive case, like majority, when you have approximation.
Okay. So in the positive case, what will happen is that if you're given a satisfiable instance, then the SDP is going to give you some biases and pairwise biases, and there'll be a rounding scheme which allows you to do better than random.
The rounding scheme, that's what I'm asking about. So is the rounding scheme?
So the rounding scheme is not always like this. Okay. Yeah. Sorry. I think I accidentally pushed the button. Okay. But yeah, maybe. Yeah. I think I'll be happy to describe it, but let's take that discussion offline.
Yeah, but that's a special case.
Yeah. This
The
here.
majority is a special case of what happens in general, only it's more complicated when it's
Yes.
an SDP and you get vectors in
Yeah,
space.
I think I've played with around what it looks like. It's just still mysterious. We can do that.
Okay. Yeah. Let's. Yeah. I'll be happy to happy to describe it later.
I guess you need the SDP, not the LP, to get for the general result, the positive.
yeah, there are certainly predicates. Yeah, for this results, yeah, I think there are examples of yeah, there were previously examples of predicates which were like balanced LTFs where the linear program failed, but the SDP was you could get you could do better than random using the SDP. And here we're constructing an example where the SDP fails as well.
But if it's not a linear threshold function, the max cut is a very good example.
Yeah, I know.
Right?
Okay.
There's a handle under it.
Yeah. Okay, so since we can't use the criterion of having a balanced pairwise independent distribution of solutions, we'll use the following more general criterion. So we're still very much using this, looking at this SDP, and what we'll do is we'll construct a perfect integrality gap instance for this SDP. Okay, so this is going to consist of a set of linear forms. And actually, I'm actually only going to need the case when they're all on the same k variables. And biases and pairwise biases. So I'm going to leave a blank space, and I'll say why in a few minutes. Such that okay, so first, for all x, if we look at any individual x, and we take a random one of these linear forms, the probability that LA of x is bigger than 0 is exactly 1/2. So not only is it possible that so not only is it hard to do significantly better than random. It's actually impossible to even deviate from random. Every x will satisfy exactly half your constraints.
This set of Riemann constraints, it's all perfect integrality get for a particular fixed p predicate.
Yes.
Right? Yeah. So we have a p in mind. It's defined only for in our form. It's not defined for any. Can the definition work for any predicate? Well, it doesn't matter. You define it for linear cycle.
Yes, but yeah, actually, you're absolutely right. So yeah, I defined specifically for linear threshold functions, but it could work for any predicate. But yeah, it is for a particular predicate. So it's impossible to deviate from random. On the other hand, for all A, there exists a distribution dA such that so dA is supported on solutions for xa. And if we look at the expected value over dA, if we look at the expected values, then it matches these global biases and pairwise biases.
So the main point is that in previous attempts, LA was just one L, the original predicate, and it could not satisfy condition 1.
So here, like this, these linear forms, like it's still gonna be permutations of the same, basically permutations of a linear form. So it's like these linear forms are gonna be like right. They still all have, these LTFs will still all have the form P.
Yeah, but you randomly switch the signs or something, or you change the signs. Here I'll permute the variables, and yeah, I guess in the final thing I will also change signs. Condition 1 for every fixed x if you are not changing the sign.
Yes, so I will both be changing the signs and permuting the variables. Okay, so
I want to say something about the values of the BIs and the BIJs.
sorry, I can't do that for the final predicate I'll get because it's quite complicated. So instead, I'm going to sketch what we do.
So you're not even producing an instance of size n. You're producing an instance of size k.
Yes.
Size k, and then the other Raghvendra result is amplifying it somehow.
That's also
Exactly. It's also what's happening here. Here, like here, this is a perfect integrality gap instance for 3 XOR. We just have two predicates. They're any assignment is going to satisfy exactly one of them, but the SDP thinks that both are satisfiable. Exactly.
The result doesn't guarantee that you can find counterexamples of size k. It might have been 200k or k to the k, right? Or is it that if the SDP fails, you can always find an instance of size k?
Excellent question. Yeah, it certainly doesn't guarantee it, and I think it's a very interesting question. Like, are there cases when you can't find this kind of example? And this is actually related to something I forgot to say earlier, which is that Bragg-Avendra gives this dichotomy, but it might be extremely hard to say for any given predicate, is this approximable or approximation resistant? In fact, it's not even known to be decidable. Okay, but yes, here these perfect integrality gap instances are. This is somewhat more general criterion which is sufficient here. Okay, so
We finish in 10 minutes, so you have to.
yeah, I'm just going to give a sketch here. I'd be happy to describe more, but that would take a lot more than 10 minutes.
Then maybe we'll ask more questions.
Okay. Yes. So here. Here's a sketch of the construction.
You are going to construct a linear function, but there is an implicit theorem that if you have the condition here satisfied, then it's approximation. Then it's approximation resistant.
Yeah, because in this case, like, I use Bragg-Avendra's result as a black box. This says that the standard SDP fails.
Yeah.
And then Bragg-Avendra's result then says it's unique games hard to approximate. Okay, so what I'll do is I'll start with a core. Which is like a perfect integrality gap instance. Except instead of considering plus or minus one variables, we'll consider variables. And instead of considering all possible inputs, we only consider a subset of possible solutions. Okay, and then we And then what we do is we take this core and manipulate it to get the perfect integrality gap instance that we want. Okay, so let me so I'll highlight in red what the differences are. So now because we're working with integers, we also have to consider the expected value of xi squared. Before it was just always 1, but now we have to consider it. Here, as I said there, so we have a subset V of z to the k, and and condition 1 is weakened so that instead of requiring that for all possible x, the probability of LAX being bigger than 0 is 1/2. And we only require this for inputs in V.
Finite set?
Yeah, V is going to be a finite set. In fact, I've written so it's still somewhat tricky to come up with, but the core with these modifications, the core is simple enough that we can come up with it directly. And here's the core we use.
The distributions dA are also supported over there, the distributions dA.
Exactly. This here is these have to be supported on V, and then they also have to match the bias for xi squared. So it's very similar to a perfect integrality gap instance, but with these modifications, and then the challenge is to manipulate that to obtain an actual perfect integrality gap instance.
I was ready to bet that monarchy was something related to this thing. Okay.
The monarchy is, I think, can be approximate.
Oh yeah, monarchy is approximable. So actually, as part of this work, I gave a simpler approximation algorithm for monarchy, which I'd also be happy to describe. However, not now.
Okay.
Yeah.